The question we are trying to address here is, what is Saint-Venant's principle? In answering this question, I'm going to consider a one-dimensional rod subjected to a point load like shown in this picture. Supposing, say, this load P is applied at a point on this cross-section. This is a pretty good approximation for what happens in reality. It's almost impossible to spread the load throughout the cross-section uniformly. It's going to be usually applied at a certain point, or maybe a very, very small area. Now, given this, what about the stress distribution inside this one-dimensional rod? Let's define a Cartesian coordinate system, x, y, z, like shown in this picture here. Say the rod has a uniform cross-sectional area little a throughout, and let's go ahead and define an average stress in the z direction. Sigma zz average equal P over A. So this is the normal stress perpendicular to these cross-sectional planes, right? The planes that are perpendicular to the z-axis. I'm going to now section the rod at three different points, points C, D, and E, and look at the internal stress distribution at these cross-sections. And this is what you're going to see. You're going to see the true stress distribution, sigma zz, is going to vary across the cross-section like shown by this red line. The closer the section to the point of application of the external load P, the more non-uniform the stress distribution is going to be. So in some areas it's going to be larger than the average stress, and other areas it's going to be smaller than the average stress. As this section moves farther and farther away from the point of application of the load, then the distribution approaches a uniform distribution. So here it is almost uniform, but not quite, but here it is exactly uniform. When it becomes uniform, the magnitude of the true stress distribution becomes exactly equal to the average stress distribution that we calculate using this formula. So here's the verbal description of what I just said. The load P is applied at a point, and the stress distribution is non-uniform in the vicinity of the point of application of the load. But as you move farther and farther away, the stress distribution approaches a uniform distribution. This observation is codified in the principle called the Saint-Venant's principle. It says, except in the immediate vicinity of the points of application of the load, the stress distribution may be assumed to be independent of the mode of application of the load. So this was first observed by the French scientist Barry de Saint-Venant in 1855, so the principle is kind of named after him. The bottom line is this. We deal with real things, real structures, real structural elements, right? If you want to analyze a member of the structure, we'll cut the member out of the structure and draw a free body diagram for it, right? When we do, the mode of application of the external force is going to differ from problem to problem. It's not going to be identical. Some of the forces may be applied at points, the others may be applied over small areas, and others may be applied over large areas, right? But the effects of this mode of application of the load tends to be localized. So in the grand scheme of things, we ignore this localized distortion of the stress distribution and go in and analyze the structural member. So this is the practical application of Saint-Venant's principle.